So we can start.
Devdar sir.
Should I start?
Yes, yes sir.
Is my video visible?
Yes sir.
Yes,
Visible.
yes, sir, we can see.
Okay.
Shubham, we can stop sharing the screen.
Okay. So it is my privilege to introduce Mr. Lotharam, our speaker for today. Mr. Lotharam is a PhD research scholar working in the Space Physics Lab Department of Physics at IIT Roorkee. His research work focuses on the loss of atmosphere on Mars and its current status. Currently, he is working on remote sensing observations of Mars during solar flare events. He has published a couple of research papers in peer-reviewed journals. Today, we have the privilege of delving into Journey Through Air, Unravelling Planetary Atmosphere, the name of his talk. Please join me in welcoming Mr. Lotharam on behalf of Wilson College Physics Department and IAPT. I am sure that all will be benefited by his insights. Now I would request Mr. Lotharam to commence his lecture. Hello, Mr. Lotharam. Can you begin your lecture?
I think he is not connected the audio. Let me message him again.
I mean, the recording is not there for him. Sorry, recording, audio nahi.
I will call him again. He is rejoining. Yeah.
Hello.
Yeah, we can hear you.
Yeah. Good evening, sir.
Yeah, good evening.
So, shall I start or?
Yeah. No, I actually gave the introduction, but I think your audio was off at that point in time.
Yeah. Actually,
So,
that's why I'm thinking like, what is happening?
Okay.
Okay.
Yeah, you can begin.
Okay, let me share my screen. Is my screen visible to everyone?
Yes.
Yes. Okay.
You can go to the screen, full screen mode.
Yeah. Is it fine now?
Yeah.
Yes.
Okay. So, hi everyone. Good evening to all of you. So, as I have not heard about my introduction part, so sorry for that. I think there is some problem with the video audio at that time. So, I am Lotram from Space Physics Laboratory, Indian Institute of Technology, Roorkee. So today, in the lecture series of Planetary Science, I am going to deliver a brief informations about the some planetary bodies and with the title of my presentation, A Journey Through Air, Unravelling Planetary Atmospheres. So in my talk, I will mainly focus on the sun and the storms which are emanating from the sun and how those storms can affect the planetary bodies over the solar system. So basically, I will today present about the three planetary bodies, Venus, Earth, and Mars, with the special emphasis on the Martian system, and also how the interaction between these bodies happen, like interaction in terms of like radiations, in terms of waves, and in terms of solar plasma and magnetic fields. So all these aspects I will cover in my presentation today. So let's start with this artistic representation of the solar system. So here this cartoon doesn't represent the whole solar system, but here I'm only just showing here the planetary bodies. So primarily the Venus, Earth, and Mars. These are the inner planets, which are the terrestrial planets, or also called the inner heliospheric planets of our solar system. And also, before delve into the information regarding their atmosphere, I will explain about the sun, because without solar atmosphere, we cannot understand like why we are studying the atmosphere and what is the purpose of atmosphere. For that reason, I'm sharing small informations about the sun atmosphere, as well as some mechanism which drive the energy over the sun. So over the sun, like inside the sun, in the core and in the outer core of sun, there are thermonuclear fusion reactions that drive the sun, as you can see in this cartoon. So this is a chain reaction which in which one hydrogen get fused with another hydrogen, so that we can get the helium nuclei and then the release of energy. So in this particular reaction, this is a chain reaction, so it involves generally the 4 protons, and these proton fuse toward make the helium nucleus and with the emissions of energy, and that energy actually that we are getting here in our planetary bodies. So so specifically, sun can emit energy in many forms, like in radiation, like in plasma, and like in fields. By fields, I mean here the magnetic fields or the electric fields, and by plasma, I mean here, as all of you were aware about that, plasma is the fourth state of matter in which we have primarily the ions and electrons, as well as the neutrals are also there, but ions and electrons we can discuss about that. So if you see in this artistic representation, like here these loops, it represent the global magnetic field of the sun, and these small loops here, these are also the magnetic loops, but these are the localized loops. Okay, so these loops actually, these are responsible for generating and emanating many storms over the sun, like for example in this case you can see in this cartoon. So these loops, so these dark spot here, as you can see in pair, these are called the sunspot numbers, sunspot basically. So these sunspots are the region where there is a high intensity magnetic field that coming beneath the sun and just passing over the atmosphere of the sun, and then due to this intensifications of the magnetic field, there is some reconnection is going to happen there. That I will show you in the coming slides how it will happen, and those reconnection will drive the energy from sun and toward the interplanetary medium, so where they can collide, or we can interact with the planetary bodies, like I have shown you here in the very first slide. So these streams of radiation, plasma, and fields, these are basically called the solar wind. So here is one of the cartoon which represent the interaction between the sun and earth. So I will not explain deeply about all these mechanism here, because I think tomorrow there is also one talk that explain about the magnetic field rule, but I will briefly talk about that. In earth we have the global magnetic field. So throughout the presentation, you need to keep in mind that the earth is the only planet out of these 3 planets, which has the global intrinsic magnetic field, means all the planet engulfed within the magnetic field. So there is a huge bubble of magnetic field around the Earth, which can protect us from the coming radiation, coming solar wind particles, as well as the magnetic field from the sun. So here, if you focus in this region, so here for information, like we have core, and inside the sun radiation zone, and then convection zone, and in this convection zone we have the convection cells there. So actually, why I'm explaining this, because this is the outermost surface of the sun, which is called the photosphere. So in photosphere you can see there is no any uniform pattern you are seeing here the granules, like some dark spots, some bright spots. So these actually represent the convection cell mechanism. Here you can see, like if you boil some water, so hot water which is less dense, so it get rise, and the cold water which is more dense, it gets sink toward the lower direction. So due to which there is circulation formation there. So same process occur in this particular layer or in this particular zone of the sun, like beneath the photosphere or beneath the sun surface of the sun. So in this photosphere, these hot plasma get rise up, and cold plasma get sink. So due to which we get these granules over the photosphere. And beside this, over this photosphere, we have the atmosphere of the sun, which we cannot see with the naked eye. We need specific filters or specific telescopic lens for that. And here you can see the atmosphere of sun, and there are also the 2-3 layers over here. What I'm only showing the most outskirt layer, which is called the corona. So in this particular layer, the magnetic field reconnection is going to happen, like magnetic loops that I have shown you in the previous slide. Those loops get interact here, so they generate the storms here. So basically what I'm explaining in my presentation, I'm explaining the relation between the solar storms or the activity over the sun. Means sun is not always with a constant, it is changing with the time. So with the changing of the time, how these solar radiation, how the solar particles, and how the magnetic field that coming from the sun try to influence the planetary body, like how the planet respond to that incoming things in terms of radiation, particles, and magnetic fields. So beside that, let me jump to this video. So I am showing currently here you the video, like in which you will see at the point of sunspots how the magnetic field intensified and how the reconnection occurred there. So this is the photosphere, and this dark region which you are seeing here, this is called the sunspots. So actually there are many number of sunspots over the sun, mostly in the equator region. So through these sunspot number, the magnetic field lines are coming beneath from the convection cell and to the over the atmosphere of the sun, and then coming back toward this region. So it acts like a north and south pole. So always these sunspots occur in the pair side, like north and south. So there are these kind of configurations over the solar atmosphere. So with the changing activity beneath the sun, like inside the sun, there is change in activity, and due to changing activity, the magnetic field lines which you are seeing here, those get intensified, or those get due to high intensifications of those magnetic field lines, they get compressed, and due to this, as you can see in this cartoon, so those magnetic field lines emanating from the atmosphere, and as you can see at this particular point, your field lines going this way and coming this way, now they are reconfigured. So this X kind of configuration, this is called reconnection mechanism. So at this particular point, actually you have also plasma there. So keep in mind, in the atmosphere you have also plasma there. So at this particular point, when these reconnection lines are happening there, so that release the magnetic field toward the interplanetary medium. So along with this magnetic field line, as you know, along the magnetic field line, you have also the charged particle which gyrate around the magnetic field line. So those plasma that is in the solar atmosphere at this particular point, that is also carried with this magnetic field line. This is called frozen in magnetic field, means plasma get frozen with the interplanetary magnetic field or the magnetic field of sun. So this specific chunk or this specific part of the plasma that get when that traversing toward the Earth atmosphere. So in Earth, as I have explained, Earth have global magnetic bubble around it. So that magnetosphere that try to, there is a tug of war between these two phenomena, like coronal mass ejection or the emitting magnetic field and plasma coming from sun, that get interactive with the magnetosphere of Earth. So here you can see this is the magnetic lines of that emitting plasma plus magnetic field. So this is magnetic field direction, and here you can see in Earth we have the magnetic field direction from here to here, like south to north. So they are both in opposite direction. So they also interact at this particular point. So another reconnection happened there. So due to which the plasma that these magnetic field lines carried with them from the sun, that plasma going through these magnetic field lines and that enter in the Earth atmosphere here, like in this region. Because here, why here? Because this is the region where the Earth magnetic field lines, this is the cusp region where magnetic field lines get sinking of the Earth or Earth system. So through these lines, plasma get injected into atmosphere and it excited the atmospheric species there. And also in the night side, we have the same mechanics here, the same mechanism happening there. And sorry for that. I'm sorry, actually, there is some problem with this video. So let me restart it. So am I audible to everyone? Actually, I think there.
Yeah, you are.
Yeah. Yes. So this is the whole phenomena, and now in the night side also the reconnection is going to happen between these magnetic field lines, and it can also bring the plasma and make the aurora over the polar region. So basically in Earth we have seen the aurora over the polar region due to this kind of interaction. So this is one of the kind of interaction between the sun and the Earth system. So now this is one kind of storm that I have explained here. This is called coronal mass ejection. Means there is ejection of mass from the corona. And another kind of storm is also over the sun, which is called the stream interaction region or the pressure pulses. So sun, as you can, if you follow my cursor, sun revolves in the direction. So solar winds are continuously emitting from the sun. So those are called the ambient solar winds or normal solar winds flow. But sometimes what is happening over the solar atmosphere, we have in the atmosphere, we have the less density of plasma there. So due to which we have the less density of plasma, so that the solar wind that coming from the sun, that is directly going through those less dense region, which we call the coronal holes. So these solar wind going in the straight direction. Like one is ambient solar wind that is continuously emitting from the sun in all direction, and one is through these coronal holes, which represented here by the these vectors, straight vectors. And here we have the curved lines also, which represent the ambient solar wind. So there is interaction between the slow solar wind and the fast solar wind. Fast solar wind representative are the straight vectors. So due to which there is a formations of compression region there, and that compression region, as sun is rotating, and that compression region is also rotating along the sun. And when it encounters the planet, it can collide with the planetary body, and due to which there is change in the dynamics of the planetary atmosphere that I will explain in the coming slide. So this is second kind of storm. So basically there are storms that coming from sun.
Hello.
And also hello.
There is one question in the chat. Would you like to take it now or at the end?
Yes, sir. It's up to you. I don't have any problem. So
should I read out the question?
Yeah, yes.
Just a second.
Hello.
Yeah, the question is the following. Why are local magnetic field lines generated why does it only get generated by sun and not by Earth or any other planet with
Okay.
magnetic field?
Okay. Actually, before this, we need to understand like sun is a star. Okay. And sun is a gaseous. A star, mostly it contains the hydrogen and helium. But if you discuss in terms of planetary bodies, like in planet, we have also hydrogen, we have also helium, but that is in lower content. We have rocks, we have another things. So basic difference it is in constituent, because sun is a gaseous body, so is a star. So that's why the magnetic field and all those things that you are saying, the localized magnetic field, that actually I have explained here in this. Let me show you. Yeah, in this diagram, as you can see these loops. So these localized magnetic field, it is not actually emanating all over the sun. It is emanating only in this part of the region. This is called the equator region of the sun. If you divide a planet or any star, like a plane divide a planet or any star between two halves, that particular part of the region is called the equator region. Okay. So in this region, actually this form near to the equator, like 10-20 degree above and 10-20 degree below the equator in this part. So that's why sometimes what is happening, it depends upon actually the dynamo of the sun, like what is happening inside the sun. So this is actually in scientific terminology, it is called the beta factor. It is actually the ratio of the plasma pressure and magnetic pressure. So when your magnetic pressure is more, so there you will get the less plasma in this region. Means magnetic field is just coming from this particular part of the region. So that's why these regions are formed, which are called the sunspot. Actually, there is a very long mechanism for this. Actually, I do not have that slide for this. So that discussion we can do in the later part also, because this is a very long discussion. So, but in planetary system, we don't have that kind of thermonuclear fusion reaction that is happening exactly in the same way as we have seen in the sun. That is a short answer to your question. So,
One just connected question, though
yes.
we may have another lecture next time tomorrow by Dr. Virendra Yadav. This is about these kind of loops are formed because of differential rotation, say, or this.
Yeah, right.
Now we also have huge gaseous planet like Jupiter, which also emits more amount of radiation than it takes, and Jupiter also has some amount of differential rotation, the atmosphere. So do we expect such kind of phenomena for Jupiter?
In the current scenario, we cannot expect, as long as I know, because like for these things to happen, we need a very, Jupiter is highly dense, as we know. But inside the core of the Jupiter, that exactly we don't know what is happening there. There are no any observation till date. Like what is the dynamo mechanism of the Jupiter? That exactly we don't know. And also for the same case of Sun, some researchers have quantified this factor about the dynamo and the differential rotation that we are talking about. But in case of Jupiter, because we don't have that much of high pressure and thermonuclear fusion is not there, because for actually for the fusion reaction or the reaction that we are talking inside the star, for that we need very high pressure and very high thermal activity should be there. So that's why at that particular point we can get the merging of the two hydrogen, because proton and proton interactions are very rare, because both have the same charge. So on Jupiter, actually till today we don't have any observations, and also we do not know how the actually core working there, core of that planet working there. Is it the completely solid or is it the completely gaseous? That exactly till date not known. So
Yeah,
for a while,
thank you. Yeah.
Okay. So shall I continue, or are there any other questions?
No, you can continue.
Okay. So these two kinds of storm that actually I have present in front of you. So after that, like how the storms, basically in the previous slide, I have focused on the storm part. And beside that, we have also the solar wind, which are continuously emitting from the sun. That is always there, which is which is called the ambient solar winds. Okay, that is also interacting in the same way. What during the storm times, actually the phenomena is intensified. So how the response of that planet to that storms, that actually I will show in the coming slides. So before that, I'm going to introduce about some planetary bodies. So in these planetary bodies, as you can see in these emojis, we have Earth, where we have the very balanced approach of life there. Everything is very balanced so that the life processes and biological processes and all the life processes can happen there. Besides Venus and Mars, which are the planets which is under the investigation these days. So there is a tug of war between the explorations on the Venus and Mars. So why is it there? Because on Venus and Mars, we do not have any global magnetic field like Earth. So how the magnetic field is different from the Earth, that we need to discuss in the coming slide. So here you can see in this specific diagram, which shows the Earth's global magnetic field. So basically, for a planetary body, in order to sustain life and in order to sustain its many physical and chemical processes over the surface and over the atmosphere, we needs over the surface and beneath the surface, we need two ingredients which are called the avengers of the planet. One is magnetic field and second one is the atmosphere. So magnetic field lecture is also, I think, Dr. Birendra sir is going to give this lecture tomorrow. So I will not go in the deep. What specifically I will discuss about the atmosphere. So second ingredient is atmosphere. So why atmosphere is important? Because in case of Earth, the first encounter that solar wind or the incoming solar storm phase, that is the global magnetic field. But in case of Venus, as you can see in this diagram, it doesn't have any global magnetic field around itself. But there is an atmosphere over the Venus. So due to that, the interactions of the solar wind that coming from the sun, that is directly with the atmosphere of the Venus, means top atmosphere of the Venus. So therefore, it needs to be understand the dynamics of that. But due to the magnetic field of the sun, those magnetic field lines here, it is shown by the yellow loops, yellow color loops. So these yellow loops here, it represents a draping of the magnetic field lines. Means magnetic field coming from the sun, it drapes the planet and make a certain kind of magnetosphere, which we call the induced magnetosphere. Means which is induced by the solar wind magnetic field. And in Mars, we have this also the same kind of magnetosphere over the Mars, which is called the induced magnetosphere. But in spite of that, we have also the localized magnetic field regions there. Like in Mars, suppose this is Mars and this is your northern hemisphere and this is your southern hemisphere. So in southern hemisphere of Mars, there are some magnetism, remnant magnetism is there, because over the crust, things like the crust material, they have the magnetic character, due to which we have the smaller loops which passing from the surface to the atmosphere and just coming back to the another pole. So those smaller loops which represented here by the blue lines, and these yellow lines represent the induced magnetic field lines of the sun. So both this interaction, it can make a hybrid kind of magnetosphere over the Mars. So that's why it is important to understand in terms of planets, like why these three planets are the very hot topic in the research. Because first we need to understand their magnetosphere, and then like in the absence of magnetosphere, how their dynamics work. So then there is a question of atmosphere come, because if there is no any global magnetic field, then the atmosphere get directly interacted with the coming solar winds, and due to that there are lots of emissions and there are lots of escaping of the atmosphere taking place in both planets. That I will show. I can show you one of the video here by NASA. So this is Venus, and here it represents the stretched atmosphere of the Venus, and in this part it is from the sunward. So here, so these loops, it represents the magnetic field of the sun, which is coming with that plasma. Okay, and this is plasma motion. So when it strike the Venus, as Venus do not have any global magnetic field. Now see what is happening. So this draping is going to happen, means these magnetic field lines get draped, and also along with those magnetic field lines, we have also plasma there. So that plasma that collide and that can also energize the upper atmospheric species over the Venus, and due to which those atmospheric species sometimes can get that much energy so that they can leave the atmosphere of the Venus. Or there is one observation from 1982 by the Cravens et al. They have found that they have observed the depletions in the atmosphere of the Venus in the night side. So from this cartoon, you can also understand, like, with this magnetic field lines, the charged particle, means the planetary charge, they can also means follow helical path around these magnetic field lines and then just scavenging or then swept away from the atmosphere. So that's why it is important to understand. So this is one of the non-mechanism of the Venus interaction with the magnetic field. And second interaction, the second idea is that if these magnetic field lines passing through the atmosphere and just entering up to the core region, like in this, as you can see here, entering to the core region. And core, we have the mostly, as our perception is, like in the core region we have the molten plasma there. So in core region, the magnetic field line get deflected and they also form the second loop here. So this is the mechanism. This is one of the possible mechanisms. So these mechanism, like first one is very well known and also testified in the previous mission, like Magellan missions and Pioneer missions. And in Venus Express also, they have testified and they have also observed the loss of the atmosphere in the night side of the Venus. But the second mechanism through the core, that is need to be understand in more detail with the coming Shukryan or coming Da Vinci missions of the NASA and ISRO. And beside this magnetism, I want to explain the little information and little primary knowledge of the atmosphere of the Venus, Mars, and Earth. So in this cartoon, you can see the Earth atmosphere is dominated by nitrogen and oxygen. So first, I need to explain here, like, what is atmosphere for the students. Atmosphere is the mixture of gases, okay? The mixture of gases that surround the planet. Like we live on the surface of Earth, and in the surrounding or in the ambience of ourselves, there is a huge blanket or huge envelope of mixture of gases, which is called atmosphere. And this atmosphere, which contains the nitrogen and oxygen in dominant role in the Earth system. But in Mars and Venus, we have the high abundance of carbon dioxide, and mostly carbon dioxide is there, and nitrogen, argon, these are in the smaller quantities also, and other trace gases are there. And beside that, one thing need to understand here, this motion, like, which I will explain in the coming slide. So this is sun, and suppose this is Earth, and this whole curved line, it represents the ecliptic plane, means it represents the path of Earth, means the planet is revolving around the sun, and the path that it traverses, which is called the orbit of the planet. Okay, so this is called ecliptic plane. In this, you can understand, this is called ecliptic plane. And when you divide the Earth system in two equal halves, so that dividing plane is called celestial equator, means the equator line, equator plane, which divide the planet in two halves. Okay, when you stretch that plane toward the outer direction, so why we are actually why I'm explaining this, because in order to understand the planetary bodies and planetary system and all the other cosmic things, we need reference frame. Like in maps, we have the reference coordinate system so that we can specify our positions and location. Okay, so in order to understand our position in space, we need some reference frame. So that's why we use the Earth as a reference, and we use this motion of the planet around the sun as ecliptic plane, which is the ecliptic plane, and the celestial equator, which is the plane which divides the Earth into equal halves. So we stretch this in the outer direction so that we can get the coordinate system. Suppose one star is here, one star is here, so that we can locate the position. So here you can see the Earth is tilted by 23.5 degree, as we have also read in our school time books. So this is the cause. This is the 23.5 degree tilt. As long as with that, if you see the tilt of these other planets like Venus and Mars, so Earth have 23.4. Mars is somewhat similar to the Earth in terms of axial tilt, but in case of Venus, as we know, Earth and Mars rotate from west to east direction. But in case of Venus, direction is opposite, means east to west. As you can see the vector of rotation. So basically, if the star following the path, like if revolve around the sun in anti-clockwise direction, then Venus is moving in the anti-clockwise direction, which is called the retrograde motion of the planet. So basically, Venus have that retrograde motion. So this tilt, why am I explaining these terms? Because this tilt actually make the seasons over the Earth. Because when it revolves around the sun, this sphere sometimes aligned toward the sun, and sometimes this sphere aligned toward the sun. So due to which we get the temperature and pressure differences, so that we have the weather system and we have the seasonal variations over the planets. So let us start with the brief introductions of the Venus. So I'm just giving the small detail of the Venus. Uh, so Venus is somewhat similar to the Earth in terms of size, and what Venus has very high temperature near to its surface, as you can see this profile. So in this profile, as this axis, it represents the altitude, means when you going from surface to the higher altitude, means toward the atmosphere of that planet. So from surface to the higher altitude, and x-axis, it represents the temperature, means what is the temperature with respect to those altitude. So as you can see at the surface, we have near to the more than 700 Kelvin temperature, near to like 500 or 550 degrees Celsius. So as long as you move in the higher altitude, the temperature get decreases. So in Venus, we have the very high density of clouds, mostly dominated by the sulfuric acid, as well as in the lower side, we have the carbon dioxide. So this system is very interesting that needs to be understood in the coming missions, like how the electric discharge is going to happen in this region, how the variations of these circulations is going to happen with change of seasons that I explained in the previous slides. And the most important part is this region, like above 100-kilometer region, because this region is a region where the planetary plasma exists. I will explain you in the coming slide in terms of Earth and Mars, then you will get know the each thing properly. So why it has very high temperature at this particular altitude? Because as I explained, in case of Venus, we have the 96% of carbon dioxide there, and due to that high abundance and dense atmosphere, there is a trapping of heat, like there is a phenomena of greenhouse effect that I think every people know. So that trapping of heat is going to happen here. So if you want more detail on that, we can also discuss later on that. So due to that trapping, we have the very high temperature at the lower portion, or at the surface or near to the surface of the Venus. So beside that, in case of our system, we have divided, because our system is very well known, because we have lots of research and lots of books published on this specific topic. So our system is divided generally into 4 spheres: biosphere, which contains all life forms, all organic life form, and lithosphere, which represent the crustal inorganic thing, and hydrosphere, all ocean water bodies, all coming in this. And fourth one is the atmosphere, which actually I'm discussing here right now. So why we are actually discussing the atmosphere, as also explained, as I have already explained in the previous slides. Atmosphere is very, very important part, which can filter the coming radiations, coming plasma from the sun and outer space. So that's why it acts like a window. So in terms of Earth atmosphere, as you can see here, we have the 5 layers of atmosphere. Generally here I have shown the 4 layer. Generally this region is also divided into 2 other parts. So the first part is troposphere, which is like from surface to the 10-kilometer height. This is called the troposphere. So troposphere, basically this is the region where all the weather system, cloud formations, circulations, and all cyclone, tornadoes that we have seen, that is all happening here. So most of the atmosphere lies in this particular part of the region. And above that we have the stratosphere, where we have the high abundance of ozone, which filter the harmful UV radiation that coming from the sun. And this is one of the important part of also the one of the important part of atmosphere. So beneath this 50-kilometer region, nearly 98 to 99% of the atmosphere lies. So most of the Earth atmosphere lie in this region. So this region, like in the troposphere, this is called the neutral atmosphere. So neutral atmosphere, where we have the more abundance of neutrals, like there are very minute or less ions there. Ions are very, very minimal. So basically neutral phenomena are there, like neutral dynamics, neutral like you solve the second law of Newton's. So with the help of that, we solve the 4 or 5 kind of equation to in order to study this particular part of the atmosphere. But above this part, like above 50 kilometer, if I show you above the 50 kilometer, we have the mesosphere and thermosphere. This is one of the important, interesting part of the atmosphere. Actually, here we have the above like 80 or 85 kilometer, we have a layer which we call the ionosphere in this thermosphere. So ionosphere is embedded in the thermosphere. So thermosphere is just starting from 100, nearly 100 or 80 kilometer to the 500 or 550 kilometer. So in this part, you can see we have also seen decrease in temperature as we move in the higher altitude, and then in stratosphere we have increase in temperature, and then again decrease, and then increase in temperature. So that we need to understand. So if someone want to discuss about this, then I can explain it in the last section, or this time we can also take some questions if anyone has some question. Then I will move to another segment. Is there any question, sir? Or
there is one question.
yes.
1 second. It's related to the magnetic field. So the question is the following: could the localized magnetic fields be due to the size of the sun? Because Jupiter and Saturn are also gas giants comprising mainly of hydrogen and helium, yet this phenomena is not noticed in them.
Okay. Initial part of the question I don't understand. Like you have told me the localized magnetic field.
Sorry, I'll read it again.
Yeah. Initial.
Could the localized magnetic fields be due to the size of the sun? Because Jupiter and Saturn.
Okay. Mainly, the question is about like the size of the sun, as well as they have tried to analog it with the Saturn and Jupiter.
Yeah.
Okay. No, there is currently no any relation between the size of because see, we cannot compare these two bodies right now, because sun is a star system, as I has already explained. So the dynamics beneath the sun, mostly that is slightly different, because in the planetary system, in case of Saturn and in case of Jupiter, we do not know about the dynamo, because inside the core of the sun, there is a dynamo process occur there. So that dynamo is very complicated. The differential rotation that we have discussed, that dynamo is very complicated. So the localized magnetic field that the student is asking about, the localized magnetic field is actually due to the sunspots. So for that localized magnetic field, we need to understand first the beneath process, like what is happening in the convection zone that I have explained in that very first slide. So that mechanism is actually right now we don't have any very deep understanding on that, because there are lots of observation that needs to become, so that we can verify the current based model. So for that part, the localized magnetic field just constrained to the sunspot. Okay, how sunspot form, that we can discuss, like, but in case of Jupiter and Saturn, that is not possible currently, because there are no any convection cell mechanism there. There is no any movement of plasma there, and also the thermonuclear reaction, which is the most important reaction, because for that we need high temperature and very high pressure, because in case of planet we don't achieve at the current moment. So that's why in Saturn and Jupiter we are not seeing those localized magnetic field region like sun. So can I move further, or are there?
Yeah, you can continue.
Yeah. So here actually I explained the 5 layers. So in these 5 layers, so here this particular part, like below 90 kilometer, this particular part is called the homosphere. Collectively we can call this the homosphere. So why it is homosphere? Because here the atmospheric constituents, by atmospheric constituent I mean the gases or the other species. Okay, so all these constituents are they have high mixing ratio, because there are high abundance or large density of all those atmospheric constituents. So due to which we have the continuously collision and the thermal processes are going to happen here. So in this specific part of the atmosphere, like beneath this region, the all atmosphere can behave like as a single quantity, because every species, means like carbon dioxide, like oxygen, they collectively response to the things. So that's why it is called homosphere. All the things are, all the constituent species have, they have same range of motion, they have the same near to the same collision ratio. So all those things depicts them the homosphere. But above this region, like above 100 kilometer, or from the 100 kilometer up to the 500 kilometer, this is called the heterosphere in this classification. Why is it in heterosphere? Because as long as we move from the troposphere, because as long as we move from the surface to the higher altitude, there is decrease in density of the atmosphere. Okay, so due to that decrease in density, the species that we have in atmosphere, there are lesser collisions. So due to that, the species have more mean free path. So means in order to collide with another species, it will take longer time in comparison to this particular part. Okay, so that's why we have the species over here, like oxygen, atomic oxygen, like carbon dioxide, or some other trace species. Those species can behave like individual species, not like as a collective atmosphere as we have seen in this part. So here, every species of the atmosphere, they behave as a single species. So every species have means different mean free path, or different scale height, as we can say, means in which they can move to the higher altitude, or there are also the movement in horizontal direction. That is different. That's why it is heterosphere. And this part is very, very important in order to understand, in order to check the dynamics, like how when the solar activity, or when there is change in solar activity over the sun, and how that activity is going to influence this particular part. Why we are interested in this part? Because this part is also the part where the low Earth satellites are also orbiting. So in order to understand like the external disturbances that coming from the sun, how they can impact in this part. So that's why the dynamics of this region is important to understand. So this region, actually, this region that I have explained in this cyan color rectangle, this region actually called the ionosphere, means in this region our ionosphere of Earth exists. So this region is also divided into another layers like D, E, F. So as so what is ionosphere actually? So ionosphere is basically the part of atmosphere of Earth or any other planets where you have the abundance of ions and electrons along with the neutrals. So now the dynamics in this region, is also controlled by the reaction between, or the interaction between the ions and electrons, ions and neutral, and electron and neutrals. But beneath this region, we have only the neutral phenomena that dominate. So that's why we have ions here. Those are actually responding to the radio waves, as we know. So that's why it is interesting to observe this region, and also the particular density in this region, like the E and F region that we have divided, in terms of density of the electrons, like how much electron density per centimeter cube in this region, how much density of electrons per centimeter cube in this particular region. So most of the electron density that till date observed in this F region. So that's why you can see here, this is the day side part and this is the night side part. I think you have many of the students have read this part also in the secondary examination, secondary courses. There is also the small introductions of ionosphere there. So in night side, we have the E region and F region. We don't have D layer exist at that time. So this region, why this region is very pivotal to understand, because in this region, all our telecommunications and all the satellite communications and all kind of satellites communication system that is happening due to this particular region. Suppose you want to send a signal to this particular point, so you just send your radio wave and it get reflected to that point. But so there are lots of service stations which can use this particular region, because today's communications is mostly possible due to this region, where the low frequency and we have multiple frequency bands of radio waves that we can send and that get reflected from this particular part, because there is difference in refractive index of this particular part. As we know, if there is refractive index change of the medium, then our wave get bent from that. So that is actually the same physics here that we have also learned in the optics part, and that's why this region is very vital. And the second part is that suppose your satellites are orbiting over this region and it needs to send some signal to the ground stations, so that signal is also passing through this region. So sometimes when solar storms came, yeah, when highly intensified magnetic field come from the sun, that can impose certain disturbances in this particular part of the region. Why? Because this region is ionized part, so that ionization respond to the magnetic field as well as the solar plasma, so due to which we are getting some hindrance in the signal that are coming from the satellites or another system at the ground station. So that's why this region need to be understand very carefully, and also this region has unique importance in terms of space weather things and in terms of atmospheric things. So this is up to the earth. Now I'm explaining about the Martian system, on which currently actually in my PhD thesis I'm working on this system, how the Mars respond to the space weather things and how the Mars atmosphere behave with respect to the space weather thing and the changing activity over the sun. So with the introduction of Mars, as I have already explained in one of the slide, it has the carbon dioxide dominated atmosphere, and also with the nitrogen and argon in the small quantities with the trace gases as compared to the Earth system. So in case of Mars, first I will show you one or two slides to like the previous missions, how we can like launch the spacecraft to there. Only the science part I'm explaining here. So in this particular part, this is the graphic by the ISRO for the Mangalyaan mission that we have launched that time. So in this part, we need to keep in mind the three things. One is the geometry, like where is Earth, Sun, and Mars. One part is that, and second part is that what is the locations of the planet at particular point of time, when you want to inject your spacecraft in that particular orbit of that planet. So here you can see in the first part, we when launch the satellite from the Earth system, we do the maneuvering around the Earth. Okay, this is called the geocentric phase. So in geocentric phase, what is happening? Your satellite use the gravitational pull of the Earth, and you just maneuver the satellite to the higher and higher orbit rate, so that it can get that much of velocity, so that it can escape the influence of gravity of that of the planet. So after it leave the center of influence, sphere of influence, which we call SOI, it enter in the sphere of influence of Sun, because Sun is the dominant body of the solar system. It has a gravitational force all over the place. So when it leaves the center of sphere of influence of Earth, it just enter in the heliocentric phase. This phase is called the heliocentric phase. And the third part is that when your satellite or spacecraft is just near to this, so that the Mars is also in that particular point. So these calculations are first calculated like at what particular point Mars is location of the Mars, and at what particular point your spacecraft is going to inject in that particular planet. So this particular orbit saves the fuel of the spacecraft, and this particular orbit scientifically called the Oman orbit. So beside that, when the spacecraft enter the Mars or any other planet, outer planets, we need to reduce their speed by putting on their thrusters, so that their velocity can decrease, because it as long as it moves toward the planet, its velocity get increases, as we have also seen in the landing of Chandrayaan. So we need to decrease the velocity. So in order to decrease the velocity, we just fire the thruster engine, and so that it can provide a force in opposite direction, and then we just orient the solar panel as showing blue color here toward the sun, so that it can get energy from that in order to make its orbit and make its energy for the another operations. So this is one of the oversimplified mechanism. So after that, the field that actually I'm working on in the Martian system, I'm basically checking the relation between the changing solar activity over the sun with respect to Mars. So for that, actually I'm using the Mars atmosphere and volatile evolution, which is called MAVEN spacecraft. This is the NASA mission in collaboration with University of Colorado and University of Berkeley. and other institutions, another institution also. So for your information, there are actually nearly 50 missions that actually done, including probes and including spacecraft missions. So there are nearly 50 missions over the Mars. So actually, the way I'm working, I'm using the data set from this specific spacecraft to analyze the Mars, because this is one of the comprehensive mission which can observe the Mars in very different way, like with the comprehensive details. So here I'm showing how it can move around the Mars, this spacecraft, and how it can take the like observations of the atmosphere of Mars, and how it check the the loss of atmosphere of Mars over the time. So here is the trajectory. So this one is the north pole of Mars, and the blue color circle or elliptical circle, this is the trajectory of the Maven spacecraft. So here you can see this light portion, this is the day side, and here you can observe there is a circular line which divide this region and this region. This is the night side, this is the day side. This is called the terminator part, which divide the two halves of the planet. So this is the orbit of the Maven spacecraft. So while orbiting around the spacecraft, Maven has means 9 instruments, and it can observe the constituents of the atmosphere, how it can vary with the time, vary with the season, and vary with respect to the solar activity. So this is one of the artistic representation of Maven spacecraft, trajectory and orbit around the Mars. And these are the instruments. So I will not delve deeply in all this stuff. So I just simply put like there are two kinds of measurement in Maven spacecraft. One is in situ measurement and one is remote sensing measurement. So in any kind of mission, you will find like these two kinds of measurements. So in situ measurements, basically the spacecraft then enter the atmosphere. At that particular point of time, it can measure the composition and it can measure the it can take the measurements from there. Okay, means in situ measurement, you should be there where you want to measure the variations. And in remote sensing measurements, there is no need to be in the atmosphere or be in that particular part where you want to measure. You just scan, or you can just send radio signals and just using your imagers or imagery things. So there are lots of ways to do the remote sensing also. So remotely you can observe the atmosphere like this. So here is terminator region which divide the day and night side, and this particular part is called the atmosphere. This is the atmosphere of Mars, and here in this direction Maven is going, and here it orient its imager toward the limb direction or the edge of the atmosphere so that it can observe this particular part. So this is the way the remote sensing measurements can be performed, and in situ measurements can be performed using the trajectory when it just entering in the atmosphere. So these two kinds of measurements are there. So in third part, this is the orbit of Maven spacecraft, means you are looking from the side view. Suppose this is your planet and sun is here, and this is day side and this is night side, and you are looking from here or here. So this is the side view of the planet Mars. This is day side, night side, and these are the different operations this spacecraft instruments that it performs, that I will not explain here right now. So now I'm introducing the atmosphere of Mars, like how it can different from the Earth atmosphere. As you can see in this diagram, we have lower atmosphere, then we have this middle atmosphere which is called the thermosphere whole part, and this is mesosphere, and this is exosphere. So the thermosphere of Mars is nearly the troposphere of Mars is nearly 50 kilometers. In case of Earth, it is nearly 10 kilometers. And also the Mars atmosphere is not means in terms of altitude, it is not that much large as if we compare it with the Earth system, because in case of Earth we have near to the 500 kilometer, 500 or 600 kilometer we have ionosphere. But in case of Mars, we have atmosphere there, but this is very means density of this atmosphere is very less in comparison to Earth. As you can see in this GIF, 100 times denser than Mars, the Earth atmosphere is. So that you can think. So in these particular layer, like this is the one of the plot that I have also shown for the Earth system. Like this is the altitude, like from here surface to the higher altitude. Okay, this is 0 to 400, and these are the electron density, means at particular altitude, what is the density of electrons. So from that we can calculate like how the dynamics is going to happen there. So the region of interest that actually we are seeing, this is the region of this particular part of the atmosphere. The similar to the Earth atmosphere that I have explained, the ionosphere part, which is the top part of the atmosphere, which encounter directly the solar winds and incoming magnetic fields and plasma from the sun. So in this part represent the lower part of the atmosphere, and this is thermosphere, and this is the exosphere. So in this part, actually we have the ions, neutrals, as well as the electron. So this top ionosphere, actually it is depleted with the span of time. Like with the evolution of time, we have seen the Mars atmosphere get escaped from here. That's why we have very arid climate in the Mars. You have seen the desert kinds of climate in the Mars. That is the main reason behind this. Is one of the factors is atmosphere, because with the span of time or with the evolution of this planet, it lose its atmosphere. So actually we are understanding why it lose its atmosphere, and what is the history of that escape mechanism, and what is the current scenario of the Martian atmosphere with respect to these solar protons, solar photons, and energetic particles and magnetic field. So here in this, so if anyone want to ask some questions, I can pick at this moment, or either I can move further. I think it appears to me like it is one-way connection, so that's why.
No, there are no questions right now.
Okay, sir. So in case of Mars, as we can see, this is in this representation, as I have explained in the initial slides. Like we have Mars, and Mars doesn't have any global magnetic field. What it has, crystal magnetic field loops here, like here in case like here. So it represents the small or mini magnetosphere. Like Earth, we have huge magnetosphere, but in case of Mars, we have mini magnetosphere. So this dynamics is also very different, the dynamics here in the absence of magnetic field. So sun emits storms and radiation and plasma. That plasma then interact with the Mars, that directly hit the atmosphere of Mars, because there is no any shield. So top part of the atmosphere that get interacted with that part. So due to which some species get energized, means the heat that transferred from the solar wind or solar protons or the radiation to the Martian species, due to that heating, the atmosphere get that much energy so that it can escape the Martian gravity, and it escape from the Mars atmosphere. This is called the thermal process, because it generate or it drive the escape mechanism through the thermal process. And there are other non-thermal processes. There are sputtering, dissociative recombination, and pickup ions. So in these three processes, basically what is happening, the plasma that coming from the sun, that actually transfer its energy to the neutral part or neutral species or ionic species of the atmosphere of Mars. So those ionic species get that much energy so that they can dissociate the another species in the atmosphere. By dissociation, I mean, for example, you have CO2 that get dissociated into O plus CO, or O2 can also dissociated into O plus O, like atomic oxygen produced. So those kind of numerous reactions will happen in that way. So all these processes can take place there. So sometimes when we have the most intensified storm, at that time these processes get enhanced. Due to that, we get more escape of Martian atmosphere from that. So this whole mechanism you can understand from through this video. Let me see. So here we don't have any global magnetic field. There is very vague atmosphere, means very less dense atmosphere. So these are the photons and the incoming protons from the protons and other plasma particles from the sun. Oh, sorry. So this is the species of Mars, like this is O2, and the incoming solar wind particle, they ionize it. So it ionizes into ions plus electrons. Now what is happening? The solar wind have also magnetic field. Now this represents the magnetic field lines of the solar wind. So through this magnetic field line, this charged particle get gyrated and swept away through this line, so that we have seen the escape over Mars. Like this. This is this. So like this, like all collectively, these processes, these collectively drive the escape mechanism over the Mars. So that's why the atmosphere of Mars is depleting with the respect of time. What currently, how it can behave with respect to these different kind of storms, and how there are variations. So one thing I want to also mention here, in solar winds, we have three kind of pressure there in solar plasma. We have magnetic pressure, because magnetic field is also there, magnetic pressure, and this represents the thermal pressure. If you follow my cursor, thermal pressure, because plasma is also always in collisions with itself, so there is also the thermal equilibrium between the ions and also the electrons. And third part is the dynamic pressure, means the plasma along with magnetic field is moving. So rho represent here the density, and the u represent here the velocity. So it represent the kinematic pressure, means the plasma along with magnetic field that moving toward the planet, and it has certain kind of pressure. Okay, so all these three terms, it generally provide a combined pressure over the Martian atmosphere. And in terms of Martian atmosphere, it has also collision between the ions and neutral species. So due to that, we have also the thermal pressure in Martian atmosphere. So now there is a tug of war between these two pressure. One is the collective pressure of the solar wind, and one is the pressure of this atmosphere, Martian atmosphere. So when there are higher solar activity, means when there are storm time, and then there are storm means generating from the sun. At that time, we have the pressure in solar wind that is very high in comparison to the atmospheric pressure of the Mars. So due to that, we have seen the compression in atmosphere, means this pressure will win and it compress the atmosphere of the Mars. So due to that compression, the atmospheric species of the Mars, they get energized and heat up, and sometimes they get that much energy so that they can leave the atmosphere, because Martian gravity is also not that much high that it can hold those particles. And also sometimes when the solar wind pressure is very low, the Mars atmospheric pressure get win and it expanded from that. And due to expansion, its altitude get increased, and due to increasing in altitude, the magnetic field of the solar wind that can swept away some part of the atmosphere. So in both form, there is escape of atmosphere is happening over the Mars. Hello. And those are the processes which generally represent the escape of Martian atmospheric species. Now the different dynamics I want to explain here about the aurora. This is very famous phenomenon. So in case of Earth, we have closed magnetic field line. So there is formation of aurora that I've explained in one of the video. But in case of Mars, you can see the global aurora. In case of Earth, we have seen the aurora over the polar region. But in case of Mars, we have seen the aurora over all over the globe. This is why, because it do not have any global magnetic field, and all the magnetic field line from sun, they carry plasma, and that plasma excite the atmospheric species of the Mars, so that they can emit also the radiations in many wavelengths. And also in the closed crustal magnetic field region, where Mars had localized magnetic field, at that point also, through these magnetic field lines, the electrons came, energetic electrons came, and they can also energize, and they can inject it in the atmosphere, and they can also produce another kind of aurora, which called the discrete aurora.
I have a question here.
Yes.
Because you have said that the high activity on the sun probably can take away some part of atmosphere from Mars. Now Mars is being observed at least for 25 years from closely, because continuously there are missions going, and within this surely there are two solar cycles, the sunspot cycles.
Right.
So how people observed that the density goes on changing, and over a long period it might decrease. I mean, are there
Yeah.
any kind of such observations?
Yeah, actually, I will show you those observations. Actually, in my research paper, I have addressed those things, the solar cycle things that you are saying. But but regarding your question, that I will also show you in the coming slide. The changing solar cycle, like the solar cycle is like of the 11 years. So in 11 years, when the solar cycle is rising, when there is like high flux of the solar photons, and also the high flux of solar protons and electrons coming, means high solar activity, when cycle is rising, at that particular time we have seen the more escape rate, because there is a principal investigator of this mission. They have recently not recently, but before 5 years, they have published a paper on that part. They have calculated the escape rate of the Mars with the higher solar activity. So they have observed that with the advancement of the solar activity, there is increase in the escape rate of the Mars, because we are getting the high flux in terms of UV radiation and in terms of protons, electrons, and magnetic field also. So due to that, we get the higher escape rate. But in the declining phase of solar cycle, like the declining phase of solar cycle, which started from nearly 2014 or 2015, when this mission actually was launched, MAVEN mission and Mangalyaan mission of India. So I have actually seen that data. I have also published 2 papers on that. I will explain that in detail in the coming slide to you. But in rising cycle, there is definitely there is escape rate enhancement that has already observed. But in the declining phase, I have also seen the enhancement in the escape rate as well as in the depletions of the Martian atmosphere. But in terms like, in order to explain the whole solar cycle, like what is the variation in whole solar cycle, that understanding is not completely done yet, because due to the observation lacking, because our mission started from 2014. After 2015, we have the good data, January 2015. So that's why we are actually in that specific point, we are at the declining phase of solar cycle. So now the solar cycle started rising from December 2019. Now actually I'm looking at data also. Is there any variation, or what is the difference between that variation? If variation is there, that actually already done in the Mars Express mission. They have also done in
So
the 2000
earlier, I mean,
earlier.
97 onwards, there
Yeah,
have been continuous every 2 year
yeah.
missions. But have they not observed these things?
Okay. Yeah, in 1997 that you are explaining, that is Mars Global Surveyor mission. That mission has also actually giving the sign of escape, but the instrumentation part there and the technical part in that specific mission, that part actually mainly devoted from different purposes. Like there are instruments, there are very good instruments. Like main purpose of that mission is to mapping the magnetism of the Mars, like what is the magnetic field of the Mars over the whole planet, like globally they want to measure. So they have also measured that magnetic field. I have also that slide if you want to see at the end of the discussion. But after that Mars Global Surveyor mission, that have also increased our understanding, because in Mars Global Surveyor mission, we don't have any in situ measurements that I've explained. Like that spacecraft will not like measure the atmospheric species when it passes through the atmosphere, because the spacecraft trajectory is different at that time. But for in MGS mission, they have used a radio occultation. So radio occultation actually I am not including in this presentation. For your query, I am explaining that they have measured the radio occultation. They use a radio occultation technique. They send the signal from here to Mars, and then they measure the electron density and neutral stuff. So from those observations, they have also observed the depletion in electron density and all those things. There are very famous paper of 2006 and 2009. They have also used MGS mission radio occultation data, but we don't have in situ measurement at that time. So without in situ measurement, we cannot confirm the thing with the proper precision and certainty. But after that, we have the Mars Express mission that have addressed many things. But the problem is also that can go up to the 300-kilometer altitude. Means from above altitude, it can just approach only to the 300-kilometer. But with MAVEN, we can just going to the means lower altitude, like 150 or sometimes 130 also. So that's why actually this mission is very, very important in that context.
Thank you.
Yeah.
There is one question in the chat.
Yeah. Hello.
That Mars is having localized magnetic field, but it doesn't have any convectional process. So, how does it get remnant magnetism? That's the question in the chat.
Yeah, remnant magnetism is actually primarily due to the actually it is believed, actually we also don't know exact mechanism behind this because we don't know the dynamo of the core. So actually in the southern side where they have measured the remnant magnetism, it is many researchers have done with the help of that MGS mission that actually you have mentioned before. Using that mission, they have measured the magnetic field there. They have measured the rocks over the southern side of Mars, like in the southern hemisphere of Mars. The rocks, they have the remnant magnetism there. So due to those rocks magnetism, these crustal magnetic field regions are there. I will show you.
Your presentation has stopped.
No. This is not actually not the part of this presentation. This is only to show. Yeah. Hello.
No, I mean, no, your PPT has stopped, I said.
No, it
Okay,
is
okay,
there,
okay.
sir. It is there.
It is there. For me, it is gone.
I don't know, but actually it is in the share mode right now. Let
Okay.
me check again.
We can see it in share mode. Yes.
Achha. No, I
Is
can't
it
see.
visible, sir?
No, not for me.
It is visible.
Can
Others
someone
also.
confirm, like,
Yeah.
are they able to see my screen or not? Hello.
Yeah. Mahesh, I'll just leave and join back.
Okay. So it is visible to others. So
Okay,
yeah.
okay. So actually, I'm explaining that magnetism part that actually you are asking. So can we discuss that in the at the end of presentation? Like I have only few slides
Fine.
left.
Yeah, fine.
Okay. So this is another kind of escape mechanism that they have observed. Till now, I have explained only the disturbances that coming from the sun or the external disturbances. So now in this slide, I'm explaining about the internal disturbances, means the disturbances in the lower atmosphere of Mars, like near to the surface, like in the troposphere of Mars. So here in this very specific geometry, you can see this is Mars, and this shaded region, it represents the atmosphere of Mars. So here, this is MAVEN spacecraft, and here is our Mangalyaan MOM spacecraft. So what they have done, they have observed the both region at the same time, because one spacecraft cannot measure simultaneously the two region of the Mars at the same particular point of time. So that's why they use the two spacecraft like Mangalyaan and MAVEN. So Mangalyaan was in the evening side, or we can say the dusk side, or the MAVEN spacecraft in the morning side, in the dawn side. So at the same time, they have measured the measurement of the atmosphere at that time, and this time aligned with the emergence of dust storm. Because in Mars, in the lower troposphere or the lower atmosphere of Mars, there are the differences in temperature and pressure gradients, due to which there are formations of global dust storm, means dust storm are formed over the global scale. So those dust storm, what they do, they can convect or they can uplift the atmosphere of Mars. So as you can see here, in this particular part of the Mars at that time, there was dust storm, and that dust storm can lift the atmosphere. So as you can see in these arrow, there is expansion in the atmosphere of Mars at that time. What in the morning side or in the dawn side, you don't see any, means expansion. So this also represent that during the emergence of the dust storm, Mars atmosphere get expanded. So sometimes it's expanded at those altitudes, so that at those altitude, like above 500, 600 or 700 kilometer altitude, those are very prone to escape, because there is the dominance of solar wind magnetic field and solar wind plasma in those particular altitude. So that's why in this particular, there is also escape is going to happen. So that is also very interesting observations from these two spacecraft. So beside this, as I've explained, I have published two research paper in peer-reviewed journal. So in both of the research paper, I have addressed the impact of storm. Like here I have mentioned CMEs and CIR. So that I have explained in the initial part of the presentation: coronal mass ejection and pressure pulses, co-rotating interaction region where fast and slow solar wind are interacting. So I have checked the variation of mass during those terms, like whether Mars atmosphere responds similar to both kind of storm or is it different. And in another paper, I have also addressed the variation of Martian atmosphere, like primary atmosphere where the plasma is very high, means rich plasma is there. During the coronal mass ejection, I have also explained in these papers. So I have not actually here put all the technical part and all the figures of my paper. Here I am only explaining these collective or the resultant figure of my paper. So in first paper, which published in JGR Planets. So in this paper, as you can see, the question that actually, sir, you have asked. So in this schematic, you can see this is Mars, this is Maven, and this is ionosphere reserve around the Mars. So this is the day side. So all the solar winds and magnetic fields are coming from this side. And in the night side, or in this specific near to the dawn or dusk region, you can see the escape. Either in the day side, you can also see the escape. So how you can means say like we have observed the depletion in Mars. So from this diagram, you can see. So the top panel represent here the day side observation. So I think you are able to see all the species here: O plus, O2 plus, CO2 plus, NO plus, and other lighter species, and OH plus, all these. This top part represent the day side observation, and this part represent the night side observation. So in y-axis you have altitude, and x-axis you have density of those particular ionic species. So this black color line, if you follow my cursor, this black color line, it represents the profile, altitude profile of those ions when there is no storm, means when there is quiet time. When there is no storm, only the quiet ambient atmosphere it has measured. And this red color, it represents the one kind of storm, which is called a coronal mass ejection storm. And second blue color profile, it represents the CIR storm, means co-rotating interaction region. So all this observation, it is I have taken this observation from onward 2015 to till 2019. Means this is the declining phase of the solar cycle that you have asked in one of the questions. So in this declining phase of solar cycle, I have observed, as you can see, in black lines we have the more density, as you can if you see the figures here. And in red part and blue part, you have seen there is decrease in density if you compare it with the quiet time. Same in day side as well as in night side. But in night side, you can see the difference is more pronounced, means this is large in comparison to the day side. So that's why in this paper, I have addressed this aspect, that during the emergence of solar storm, specifically the CME and CIR storm, like stream interaction region and the coronal mass ejection, during that time, we have observed the depletions or the loss or escape of Martian atmosphere in both day side as well as in the night side. And this escape, as you can see in this diagram, it is more pronounced in the night side and in the higher altitude, like above 200 or 250 kilometer altitude. And in the second paper, if you see this collective figure, I have considered here the 8 solar storm, 8 coronal mass ejection event. This is 1, 2, 3, 4. So 8 coronal mass ejection event. I want to check like whether it is the general trend or is it constrained to the specific storm. So here you can see the blue color profile represent here the quiet time profile, means when there is no any coronal mass ejection or solar storm. And the red color profile, it represents the storm time profile, means when there is storm passing through the mass. So as you can clearly see, the density of this of the electron, means electron density get decreasing, and also it gets shifted slightly to the our altitude. This mechanism we have actually explained in detailed in our paper. So, oh, I'm sorry. So from these analyses and from the previous studies also, we can say that Mars atmosphere is escaping, and that escape rate of that depletion is more pronounced during the onset of the solar storm or during the solar storm. So these are the all observation, but we have certain observational constraint which constrained us to quantify and which constrained us to fully grasp the picture of the Mars and other planets. So that is the observational constraint, because we have only one spacecraft that cannot measure the same thing at the different location at the same time. So that's why we need multi-point spacecraft observation in the future missions. And also we need ground-based as well as the space-based observation. Like we have probes over the Mars, so we can communicate with probe as well as with the orbiter spacecraft so that we can measure. So in this cartoon, you can see here is Mars. If you want to see any person, location of that person, we need at least 3 satellites. Like that, if we have 3 satellites in the geostationary orbit, like over the equator, so we can measure the collective picture of the Mars with respect to this stone, means more comprehensive picture. So these things need to be addressed in the future missions. And also these are the upcoming missions of ISRO India. So Gaganyaan and NASA ISRO synthetic aperture radar, and Shukrayaan, which is going to address the various mysteries of the Venus atmosphere, as well as the Mangalyaan mission 2 and the X-ray polarimetry satellite, which can observe the cosmic things like the black holes and stars and emissions from stars in the band of X-ray. So all these missions will collectively enhance our understanding in the coming days and in the coming years. So beside that, here, Indian Institute of Technology, Roorkee, we have also 2 designated lab and center. One is Space Physics Laboratory, where actually right now I'm working, of the Department of Physics. So this laboratory has a high altitude optical aeronomy observatory over the Leh Ladakh region in the Indian Astronomical Observatory, telescope near to the telescope. So here, what this aeronomy observatory done, it observed the emission profile of the Earth upper atmosphere. So my lab members are working in this particular region. So anyone interested, he or she can also apply after graduation for projects as well as for doctoral degree. And recently, IIT Roorkee also started the Center for Space Science and Technology, which is dedicated center for planetary science, technology, engineering. All this stuff has been incorporated in this specific center. This is also now in operational mode. So from this year, you can also apply, any students, if they want the further academic studies in this specific domain. So they can also apply there. So beside that, for all this research specifically related to the Mars, I want to especially thank the NASA and Niven team who collaborate, who guide us throughout this journey, and also Professor Paul Withers, Helikus, and my supervisor, Dr. Suman Sarkhel, and Dr. Deepti Ranjan and Dr. Virendra Yadav for their mentorship. And lastly, I want to acknowledge the Ministry of Education for this support. And finally, I want to also thank you, the Wilson College, Mumbai, in collaboration with the IAPT, Mumbai, that they have given me this opportunity to share my research as well as the fundamentals to the planetary atmosphere. And lastly, I want to leave all of you with this quotation, famous quotation of the Carl Sagan: "Somewhere, something incredible is waiting to be known." So that is the basic essence of our space and planetary science. So I want to thank you all of, I want to thank you for your kind attentions. So any questions and any discussion will be welcome.
Yeah, there is one question.
Yes, sir.
By Mahesh Shetty. Do we expect similar kind of atmospheric escape for Earth?
Earth. Okay.
Yeah.
Currently, in case of Earth, there we cannot expect like Mars, because Earth is, first thing, Earth has dominant magnetosphere. That is a main point. And the second point is that Earth has strong atmosphere also. So these both things can collectively are the main dominant factors or the guardians which guard the, this planet. So right now we cannot expect, but yes, there are some studies here they have seen escape of O+ through the magnetic lines. Like sometimes some storm can deposit their energy in the ionosphere, so that some ions, they get gyrated around the magnetic field lines and then they escape through these. So that can happen through the open magnetic field lines. But at the instant of like in context of Mars, that is the different picture, because we don't have any strong magnetosphere there. That is the main, and also atmosphere is also not that much dominant there. So that is the reason. But in the long run, using the Mars observation and the Venus observation, we can understand like what would be happen in case of Earth if it lose its magnetosphere, like it lose its magnetic field. That is now question of the core region of the Earth, like how the core circulations will work and how the decrease in magnetic field there. That is very, I think, long span of time. So currently there is no possibility of escape like Mars.
Thank you, sir.
Yeah, thank you, sir. And
are there any other questions?
yeah, if there are any other question, then
let me just check the chat. There is one more. Is it true that strong solar wave is going to hit Earth and is it going to break the magnetic field of the Earth and destroy some electronic devices we use on Earth?
yeah, it could be happen. Right now, I think all of you, I don't know whether you have heard or not. 1859, there is a Carrington event there. There's a very highly intense geomagnetic storm came, and that geomagnetic storm actually totally black out the all electronic system of at that time, because at that time we don't have also that much electronic gadgets and all those things. But the totally blackout in we have yeah, like the researcher have observed at that time. But it could be happen in the future also. I think last week there is a storm, radio burst from the sun, that is also black out the certain signals at some particular point of time. So that could happen, yes. When there is very highly intensely geomagnetic storm, that can totally compress the magnetic field of Earth, and there is a very strong impact on the electronic system and telecommunication system. Most it impact on the higher altitude satellite system, like which orbiting in the low Earth orbit, which are the communication and telecommunication satellite, and also the astronaut, like in the international space stations. They are more vulnerable to these particular radiation and magnetic field variation. That could be possible, yes.
Just check once more. No further questions.
Can I stop the presentation?
Yes, yes. Okay. So I'll propose the vote of thanks. So on behalf of Wilson College Management and the Physics Department and IAPT, I extend our heartfelt gratitude to Mr. Lotharam for such an enlightening and thought-provoking lecture. Your insights on sunspots, induced magnetospheres over various planets and atmospheres of different planets have broadened our perspective. We all are immensely grateful for the time and effort you have invested in sharing your expertise with us. Your passion for the subject has inspired us all. Thank you for your wonderful lecture. Thank you.
Thank you, sir, for the invitation.
Shubham, we can stop recording and the link.